Hi everyone. In this video we're going to go a little bit over the final project. Below in the video description you will find a few different outlined areas and different times at which we go over those things. So it's basically broken into 4 parts, and we will talk about just the general information, that's what this is, and then we'll talk about the 4 parts. So the first thing that I wanted to do was go over some very general information about the project and basically let you know what your challenge is. Now, I do want to be very clear with you that some of the things that we're going to do in this project are not realistic to the way that scientists might try to accomplish these goals, but they're more designed to incorporate some previous experiments that you've done so that you can independently design your own experiments to find, unknowns and things like this. So that's basically how this project was designed. So don't feel like this is how the New York State Environmental Protection Agency would actually calculate these types of things. And also the experimental limits that we are giving you for concentrations of things like nickel and cobalt in water are a little higher than would be acceptable. But it is a concentrated sample, so we did make that up. Anyway, I just don't want you to think this is some realistic thing that we found out of a paper or something. It's a bit of a project designed for a general chemistry class. All right, so what we're looking at is the New York State Department of Conservation recommendations for certain metal acetates and acetic acid found in a concentrated lake water sample. So essentially you are going to be provided with 2 things. You are going to be provided with a solid metal, transition metal acetate compound, and you're also going to be provided with a concentrated unknown, and you are going to do several things in order to test it out. So the acetates that you could be provided, if you're in team 1, it'll be copper acetate. In team 2, it'll be nickel acetate, and in team 3, it'll be cobalt acetate. 4 and 5 are repeats of copper and nickel acetate at different concentrations. You are also given the New York DEC recommendations on the maximum concentration of the transition metal acetate in the concentrated sample. Those are given here. And you're also given an acceptable pH range between 4 and 9. Again, this is for the concentrated sample, not for the actual lake water. So these are basically what you're going to compare them to. Well, how are you going to find these maximum concentrations of the transition metal acetate? Now, what we're going to do now is I'm going to talk about this very generally in the introduction, and then I'm going to talk about it in much more detail, and Timon is going to talk about it as well, in each of these individual sections. So the first thing is you're going to find the concentration by spectroscopy. These metal acetate solutions absorb visible light. Said another way, they're colored solutions. And you are going to determine through absorbance, as you have done before, the concentration of each of these acetate solutions by spectroscopy. You're also going to do it by conductivity. These metal acetates are salts, so therefore they conduct electricity, and concentration and conductivity are related to each other, and you're going to make a calibration curve just like in the spectroscopy section, and you're going to determine the concentration of the acetate solution by conductivity as well. This one's a little bit weird, but you're actually going to determine the experimental Van Hoff factor as a way to prove sort of that the metal acetate solution that you think you have is actually present. So you're going to do this in 2 ways. You're going to do it by the lambda max of the spectroscopy section, and you're also going to do it by the experimental Van Hoff factor. This is one of those things that's not realistic, a realistic way of proving this, but we're not going to use an ICP-MS. So basically, this is a reasonable way to do it in this case. Finally, you're going to do the pH of a buffer solution. So this solution not only contains acetate, but it also contains acetic acid. And therefore it's a buffer because it has a weak acid in its conjugate base. And you are going to go ahead and determine the experimental pH, and you are also going to determine the actual pH by literally sticking a pH probe in there, and you're going to compare those 2 values and see if they're within the DEC's acceptable pH range. So that is a very brief overview of what you're going to do, and again, we're going to talk about each of these sections in much more detail. The final thing that I want to talk about is a little bit about the project logistics. So you're going to be assigned to teams of 3 or 4 students in your lab. Correction, that is 4 or 5 students. It says it right there, and I said 3 or 4, and it says 4 or 5. But you're going to be assigned to teams of 4 or 5 students in your labs, and each team is going to complete this project. So not each team of 2 that you're used to working in is going to complete all of this project. So essentially, there are 4 parts and 4 group members, maybe 5. So you might have 2 group members do the pH section, for example. But you're going to basically break it up and break up the work. You are going to be required to write a lab report, okay, that will be having an objective, a hypothesis, variables, all the usual sections, and you're also going to have an introduction that you're going to do it as a pre-lab, and I'm going to talk about that in a minute. You will be graded on your precision and accuracy. Your calibration curve should have R-squareds of 0.99 or better. We're going to compare it to the experimental results that we got, and it should be relatively close to what we are experiencing. So, for example, if we find the pH is 4 and a student finds it's 12, that's not very close. But if we find that it's 4 and they find that it's 4.5 or 5, we're not going to be super picky about this. But it needs to be relatively close to staff-generated data. Said another way, if something doesn't work, do it over. All right, presentation, you will give a presentation on this, and we will have a separate video where Tim and I go over the presentation, but that's way off. This is not where we're getting you ready for here. Here we're getting you ready to do the experiment, so don't worry about the presentation for right now, and then you get a participation grade. So make sure that you come to lab and work well with your team and do what you're supposed to be doing, and then you'll get full credit for that. So what are we actually going to do? The first day of the project, your TA will briefly introduce the project, and then you'll have about 2.5 hours to get started on the project. So you're going to want to hit the ground running. So you're going to want to have an idea of which part of the experiment that you're supposed to do and how to do it. So we'll talk about, again, each section of the experiment in a little while here, but that's basically what you're going to do. Project day 2, same thing, except you're going to continue with whatever you didn't finish on project day 1. Project day 3, you're going to use the first half of the class to finish up any experimental stuff that at the last minute you found something on project day 2 that wasn't working or whatever and you didn't have time. You could finish that up on day 3. Ideally, however, you're going to use the first hour and a half of project day 3 to work on your presentation. The second half of project day 3, you're going to give that as a practice presentation so that your TA can give you feedback and you can improve your presentations. And then finally, project day 4 is the real deal presentation that counts, and staff members will visit most of those presentations, not necessarily all of them. Okay, so that is basically that. What you're going to do the very first week of class. What you're going to do this week is basically coming up during the final experiment, the buffer experiment, is you're going to get broken up into your teams. So we're going to use the time for recitation to break you up into your teams, and each team is then going to have to decide for themselves how they want to break up the work. And again, we're going to talk about each part of the experiment. So we have the 4 parts of the experiment. So first of all, we have a place for you to put each of your team names and your email addresses so you can all contact each other, and then who's going to do what, and then some general notes like how you're going to do this. You're going to use Google Docs, who's going to do what. You are going to have a fairly extensive pre-lab that is due the first day. We're going to talk about the pre-lab for each individual section of the experiment when we talk about the individual section of the experiment, because it's far too much detail to go into here. But you are expected to have a single pre-lab for the whole team. That does not mean that each person has to do the whole pre-lab. It means each team has to do the whole pre-lab, and you should essentially break it into 4 pieces. And then each team member can do one of the pieces, and then you can all work on deciding who's going to put it all together and hand in a single comprehensive document. I do want to let you know up front that the pre-lab for this project is not much, but somewhat more extensive than the pre-labs that you've done in the past. So please do allow yourself some time to work on that. But also note that it's doing 2 things. One, it's the only pre-lab of the entire project, so you don't have a pre-lab every week, which means you'll have no pre-lab for the final 3 weeks. And the second thing for the project, which is 4 weeks long, is that this will set you up really well for your presentation. So if you spend some time on your pre-lab, you can use the same information I mean, you'll have to type it into PowerPoint, but it'll be the same information again in your presentation. And of course, your presentation will include other things as well. So that is basically that. So the pre-lab will count as about 40% of the lab report letter grade. You know, it's a letter grade, so we're going to use it as about 40%, so a little less than half. So you do want to spend some time on your pre-lab. Your pre-lab will have an introduction, that's new, we'll talk about it, hypothesis, that's not new, experimental procedure, and chemical hazards and waste. So the usual stuff for a pre-lab, with the exception of this introduction piece. And each introduction for each section has some very specific details that, again, we will talk about during the each individual section of the experiment.
So the first section of the experiment, experimentally, that I'm going to talk about is the concentration by spectroscopy. So essentially there are two things I want to go over here, kind of three things, but really two things. One is the experimental procedure that you're going to follow or come up with in order to determine the concentration by spectroscopy, and the other thing is what you're going to write in your pre-lab, namely the hypothesis and introduction. But first I'm going to start with the concentration in the experimental procedure in order to give you an idea of what you physically will be doing in the lab first. So what are we going to be doing for the experimental portion of this experiment? Well, essentially what we want to do is we want to make a calibration curve of our transition metal absorbances, and we want to use that to determine what the concentration of the concentrated solution provided to you in the lab is. So this is very similar to an experiment that you did earlier in the semester when you had to make a calibration curve of red 40 food dye and determine the concentration of an unknown solution provided by your TA. So it would probably be in your best interest to reference back to that experiment when trying to figure out exactly what you're going to do. But for the purposes of this video, I'm going to walk you through a good place to start for your experiment and how you can use that to work towards getting your final data. So in the actual paper that will be available to you on Blackboard, we go through a variety of questions that help guide you on both the introduction portion and the experimental portion. So for the experimental portion, it asks you some questions about the molar absorptivity and molarity and molality and various things. And these are questions that you should take into account when designing your experimental procedure, but they won't give you exact numbers that you should use when working towards your experiment. So what I'm going to do is give you some exact numbers that you should work with in this experiment. Now, it's important to note that because we're eventually going to be using these values in order to determine an experimental von Hoff factor, that we need to actually work in molality and not molarity. So for the sake of making our solutions, we're going to be doing them as moles per kilograms of solvent rather than liters of solution. So the first thing that I'm going to recommend to you is that you make a stock solution. So what solution are we going to make for this experiment? Well, I'm going to, rather than have you kind of guess at what the stock solution should be, I'm going to give you some values for a stock solution that you can make in the lab. So the stock solution that everyone should make to start is that they should use 0.5 grams of transition metal acetate. And I say 0.5 and not 0.5000 because you don't need to have that kind of precision, but it is important that whatever mass you do get, you write down so that you can actually calculate the molality. And what you're going to do is you're going to add that to 100 grams of water as your solvent. So now once you've got your grams of metal acetate, which you can convert to moles, and you'll have your 100 grams of water, you can determine the starting molality of your solution. Now, that solution will definitely absorb higher than the linear range. If you remember back from the earlier spectroscopy experiments, the linear range of absorbance is, generally speaking, between 0.1 and 1. So, how do we go from a solution that's too concentrated to a solution that falls on this range? Well, the answer is very simple. We're going to dilute it. But the question is, how much should we dilute it by? Well, this range, if you'll notice, is exactly a factor of 10, right? Zero point 0.1 to 1 absorbance unit is exactly a factor of 10. And we know from previous experimentation that in that range, the absorbance is linear. So the concentration of this solution should be exactly 10 times the concentration of this solution, give or take some experimental error and, of course, variance when you do your experiment. So that means we can dilute solutions tenfold at a time in order to never skip this entire range. Because even if we're at exactly 1.0 and we dilute 10 times, we'll end up at 0.1. So if we're at all above 1.0, which we should be if we're going to keep diluting it, then diluting it 10 times can't skip this entire range. So what you should do is you should measure the absorbance of this solution. So the first thing you're going to do is you're going to measure the absorbance of stock solution. And that stock solution is going to be too concentrated, but it's good to do that just to make sure that it is too concentrated and you haven't made any mistakes. Now what you're going to do is you're going to dilute it 10 times. What do I mean by dilute 10 times? I mean add 1 ml of stock to 9 mLs of solvent, in this case water. So diluting it with 1 milliliter to 10 milliliter total volume will dilute the concentration of your solution by 10 times and bring it closer to this range. And then you're going to repeat until your absorbance is 0.1 to 1. So you'll repeat this process of diluting 10 times until your absorbance falls on the linear range. So once we figure out that our absorbance is on the linear range, how do we figure out how to make our actual calibration curve solutions? Because of course this will only give us 1, and if we end up at something like 0.3, then that'll be too low on the calibration curve to satisfy the experiment, which needs you to have a range of absorbances across this entire range. Well, we're going to use a little bit of math in order to do that. So I'm going to make up some numbers and do the math in order to figure out, in order to show you an example of how to figure out what concentration you'll need. So let's say that while doing this, we find that an absorbance of 0.350 is found or measured in a solution whose concentration is 2 times 10 to the negative fifth molal. So we've figured out that that is a true statement based on the work that we did in the experiment. So now we want to figure out how to make a solution whose absorbance is around 1 molal. So to do that, we're going to set up a proportion. So because we know that the absorbance is linear over this range, we can say that as 2 times 10 to the negative fifth molal is to 0.350 absorbance units, some concentration X is equal to an absorbance of 1.0. So we can set up this equality. If we multiply, cross multiply, we need to multiply these two things and these two things. We find that 0.350 times X, our concentration, is equal to 2 times 10 to the minus 5. Because 1 times 2 times 10 to the minus 5 is, of course, still 2 times 10 to the minus 5 molal. Now we divide both sides by 0.350 to cancel it out on the left side. And we find that our concentration should be about 5.71 times 10 to the minus 5 molal. So that means that if we make a solution whose concentration is 5.71 times 10 to the minus 5 molal, it should be at an absorbance value of around 1. Now, we should not try to make that from solid. If we try to make that from solid, it's going to require an extremely small amount of salt or an extremely large amount of water. So what we're going to use is we're going to use our stock solution. And we're going to dilute some of our stock solution in order to make this new sort of stock solution. Once we do that, we can dilute it to an 80%, a 60%, a 40%, and a 20% solution, which will give us 5 data points, the 100, 80, 60, 40, 20, for our calibration curve. Now, it is important to note that this stock solution is actually not going to be used by just the spectroscopy students in this experiment. In addition to the spectroscopy portion of the experiment, the conductivity portion of the experiment will also be using this stock solution to start with. The good news is that you're going to make 100 milliliters, and in order to make your first diluted stock, you'll need a total of 1 milliliter each, so you'll have 98 milliliters left with which to make your absorbance of one solution, which should be more than enough for you. So, now that I've talked about the experimental portion of the spectroscopy experiment, I'd like to talk about the pre-lab portion that you're going to have to do for the first week of lab. So if we go back to our document that you'll have available on Blackboard again, you'll see that we have a concentration by spectroscopy introduction section. And in this section, we give you some rules that it should be about 1 page long, that you can use figures, that you need to cite things if you take anything from the lab manual or from a web page, we specifically state that figures do not count towards the 1 page, so don't try to simply add 2 large pictures and only write 1 sentence for your introduction. So an introduction is something kind of new to you as far as a lab report goes. And the purpose of an introduction is to give a brief background on the topic that you're going to be discussing to your audience. So you're going to be assuming that that our virus and threat protection is not out of date, but you're going to be assuming that our audience doesn't have a great background on the spectroscopy, so you're going to give them a brief background. So if you notice in here, it'll give you sort of a guideline, but it specifically says that submitting a list of answers to these questions, even if each of those answers is a complete sentence, it will result in a grade penalty. Said another way, you need to write this as though you were writing an actual paragraph and not just a collection of loose ideas. So if you look in here, it asks you things like, what is Beer's law, and how can you use that to find concentration of solutions? It wants you to talk about, it suggests that you maybe look at the general chemistry manuals for how you can estimate concentrations, and what your linear range is. It also suggests that it may not be a bad idea to look up the molar absorptivity of your compound and talk about that in your introduction. But basically the idea here is you should give a brief idea of what absorbance is and how you can use spectroscopy to measure the absorbance of your solution. So the last thing I want to talk about is the hypothesis for this experiment. So a hypothesis generally needs you to make a prediction and a scientific reasoning for that prediction. Well, in this case, you're going to use the values given in the project material to make your prediction. So if we scroll back up here, we'll see that the maximum concentration of the transition metal acetate as allowed by the NYDEC is here in the file. So generally, we should make our prediction that the concentration will be something less than the value of the maximum concentration allowed for your transition metal acetate. And the reason for that is simply that we don't want to assume that the company that's putting this into the lake is breaking the law until we prove that they do so. So we want to make our prediction that the concentration will be lower than that value. As far as the how and why of the hypothesis, well, that's everything we just talked about over the last few minutes. You're going to make your calibration curve, you're going to measure the absorbance, you're going to find the concentration, etc. So, the full portion of this will take a little bit longer than you're used to, but hopefully this information will help you kind of formulate an idea of what you're going to do before you do it. So you'll notice that while going over all of this information, I didn't give a lot of very specific details, and I left a lot of things kind of vague, and that was mostly on purpose because the purpose of this experiment is to get you to think about what you're doing and kind of work through how to do it on your own. That's not to say that we're going to leave you completely in the dark on anything, and if you are struggling with ideas or you need help, you're more than welcome to ask a TA or a staff member at their office hours, and they'll help you figure out where you need to be. But we don't want to just give you all of the experimental procedure and background information for this one, as that's kind of the point of the project. So that's it for the spectroscopy portion, and next we will move on to determining the concentration by conductivity. So the next section of the experiment is the conductivity measurement by concentration. Or rather, the concentration by conductivity. So in this portion of the video, I'm going to go over two things primarily, both the introduction, as far as what you need to write in the actual lab report alongside the hypothesis, and the experimental procedure for what you're actually going to do in the lab. Now, if you open up the file that's available, the copy of this file that's available to you on Blackboard, you'll see that there's a variety of questions that give you a sort of guideline on how to approach your particular experimental procedure. So if you look through, you'll see it says what concentrations are you going to make, will you do it in triplicate, how will you clean the conductivity probe, all these sort of standard questions that are normally covered by the material we give you in the lab manual, you'll need to come up with to a certain degree on your own. Additionally, for the introduction, there's a variety of questions as well, which I'll go over in a few minutes. The first thing I want to go over is the experimental procedure for this portion of the experiment. So this portion of the experiment is very similar to one of the experiments that you did in General Chemistry 1 when you measured the conductivity and made a calibration curve of salt solutions in order to determine the concentration of an unknown solution using a calibration curve. So you're going to make a calibration curve in this portion of the experiment. But how are you going to make that calibration curve? Well, the first thing you need to do is you need to make a stock solution. So the stock solution, I'm going to give you some guidelines on and give you some advice on how to use that stock solution in order to find the range of your calibration curve. So the stock solution should be made by taking 0.5 grams of your transition metal salt, and you're going to add that to 100 grams of water. Now you'll notice I said we're going to add it to 100 grams of water. We're not going to add it to a certain volume of water because we need to do this portion of the experiment in molality. The reason we need to do it in molality is because later on in the experiment, the Van Hoff factor calculation, that equation uses molality and not molarity to perform its calculation. So your calculations will need to be done, or your calibration curve and measurements will need to be done in molality, not molarity for this portion of the experiment. So we're going to take 0.5 grams of our transition metal salt. You'll see that I've only used one sig fig, but that's just to indicate to you that it's not important that you get exactly 0.5000 grams, just that you get around a half a gram. And you're going to add that to, again, around 100 grams of water. While the exact numbers that you use don't need to be these specific numbers, it is important that you write down the exact numbers you use so that you can calculate your exact concentrations. So, you're going to take this solution and you're going to measure its conductivity. And because I didn't, since kind of the point of this experiment is that you'll need to do some of the experimental work on your own, this measurement should be well over your range, which in this case, the range you're looking to measure on is 2,000 to 300 microsiemens per centimeter. So you're going to measure your conductivity on this choice in the microlab, and you're going to find that it's too concentrated. Well, it's too concentrated, so what do we need to do? We need to, as I just kind of said by accident, we need to dilute it. So we're going to dilute it by tenfold. Now, why have I chosen tenfold? Well, if you'll notice, this is our linear range, right, between 2,000 and 300 microsiemens per centimeter. That range is almost exactly tenfold. So that means that if we end up anywhere above this range, even if we get right to exactly 2,000 microsiemens per centimeter, and we dilute tenfold, we should still be on this range. So by diluting tenfold at a time, we should not be able to overshoot the entire range from above 2,000 to below 300. So by diluting tenfold, we can try to ensure that eventually we land somewhere on this range. So how are we going to dilute tenfold? Well, we're going to dilute 1 ml of our stock solution into 9 mLs of solvent, in this case water. So we're going to take 1 milliliter of this solution, we're going to add it to 9 milliliters of water, and we're going to use that as our next step in our work towards finding something on this range. So again, we're going to measure the conductivity of this solution, and then we're going to repeat the whole process from diluting and measuring the conductivity over and over again until the conductivity is somewhere on our 2,000 to 300 microsiemens per centimeter range. So eventually we will get a measurement that is somewhere on this range, and that will allow us to make our calibration curve. Now, odds are pretty good that you're not going to end up with a solution that has a conductivity of exactly 2,000 microsiemens per centimeter. So if you end up with something that has a lower value and you need to create a solution that covers the whole range, as covered in the instructions for this portion of the experiment, you'll need to figure out how to do that. So how do we do that? Well, let's say, and I'm going to make up some numbers here, that we measure a conductivity of 750 microsiemens per centimeter. And we find that that concentration is 2 times 10 to the minus 5 molal. Now we can use this in order to help us calculate what concentration will have a conductivity of 2,000 microsiemens per centimeter. So to do that, we're going to set up a proportionality. So we can say that 2 times 10 to the minus 5th molal is to 750 microsiemens per centimeter, as some concentration X is to 2,000 microsiemens per centimeter. So now we're going to cross multiply. We're going to take this and multiply by here. We're going to take this and multiply by here and see what we get. So we'll see that 750 microsiemens per centimeter times X is equal to 2,000 times 2 times 10 to the minus 5, which times 2, and then we're going to move our decimal point over 3 places. So it's 2 times 10 to the minus 2. So if we take our both sides of this equation and we divide by 750 microsiemens per centimeter, 750 microsiemens per centimeter, we'll find that our concentration X is equal to about 5.33 times 10 to the minus 5th molal. So now we can use our stock solution and dilute it to a concentration of 5.33 times 10 to the minus 5 molal using our dilution equation. One thing I want to point out is that this solution is not going to just be your stock solution. It will only be used by your group. However, it will also be used by the spectroscopy people in their portion of the experiment. In their portion of the experiment, I told them the exact same thing, so that you'll both have this stock solution to use. The good news is that you're each only going to need 1 milliliter of that stock solution doing your dilutions to end up on your linear ranges, and then you'll both need some of the solution to make your stock solution at the top of that linear range once you figure out what that should be. So the 98 remaining milliliters should be plenty for both of you to make your stock solutions. So this is an idea of how to start your conductivity portion of the experiment. So now I want to talk about how to do the writing portion of the experiment, where you talk about your introduction and your hypothesis. So, as I said before, the file that's available to you does show you a series of questions asking you about your portion of the experiment in order to give you some guidelines for writing your introduction. So the first question should be, well, what is an introduction? You haven't written one before. So an introduction is something that we put into papers that we write for chemistry to give a background set of information to the people reading our paper. Because not everyone who's reading your paper has a full background in conductivity, you want to make sure that you give a background to your audience so that they are on a good footing to understand the rest of what you're going to say. So the introduction for your case should be about 300 words, about one page, and it should talk about determining the concentration of the transition metal acetate by conductivity. It's important that anything you do in here, such as figures or some things from a website that you might find, that they're cited. We want to make sure we're not plagiarizing other sources. This includes the lab manual. If you use a figure from the lab manual, please be sure to cite that in your paper as well. But it's also important to note that the figures that you might use do not count towards your one page, so you'll need one page just from your writing, which again should be around 300 words. So, the introduction should talk about a set of background information. So, towards that purpose, we have a series of questions here that can help you formulate that background. Things like, what is a conductivity meter? How does it work? What's a strong, non, and weak electrolytes? What type of electrolyte is our material? How does it affect conductivity? Etc., etc. So these questions are provided as a way for you to have a basis to write your introduction. It's important to note that, as it says in this paragraph, submitting a list of answers to these questions, even if you put them in the form of sentences, is not sufficient. You will need to write more than that and make it an actual coherent paragraph that can be read without knowing exactly what these questions are that were asked. In addition to your introduction, you'll also need to write a hypothesis. Now, a hypothesis, as we all know from writing several of them during this course, should have a specific prediction of our results and some scientific reasoning for why we think that'll be our result. Now, for your specific prediction, what you should do is you should go back to the NYSDEC limits provided in the file found on Blackboard, and you should assume that the concentration of your concentrated sample will be below the maximum allowed amount by the NYSDEC. The reason for that assumption is we don't want to assume that the company is breaking the law until we prove otherwise. So to start, we want to assume that they have followed the guidelines and that the value will be below the acceptable limit. So that's the prediction we want to make in our hypothesis. Once we've made the prediction, we need to provide some scientific background and how we're going to actually prove that. And that's everything I've just talked about for the last 10 minutes. Your calibration curve, measuring your conductivities, determining the concentration of the concentrated sample by that conductivity, etc. That will be your scientific reasoning for how you're going to find what the actual concentration is. So, in all, I hope that this helps you write your conductivity portion of the Prelab and come prepared for the first day. You'll notice that throughout this portion, I've been a little vague about the specific details and some of the things you're going to do, which is intentional because we want you to figure out what you're going to be doing. That's kind of the point of the project, for you to act as a scientist and develop these things on your own. So we'll leave that the specifics of those things to you to figure out. That said, we're not going to just completely abandon you for this portion of the course, and if you do have questions and get stuck, then you are more than welcome to come to staff or TA office hours in order to get some help with the things that you need help with. So, good luck on your experiment. Next, we will talk about the freezing point depression and Van Hoff factor portion of the experiment.
So in this section, I want to talk about the freezing point depression and the experimental at Van Hoff factor. So what I'm going to do generally is talk about the experimental procedure first, and then we'll talk a little bit about the introduction and the hypothesis. So the first thing that we want to do for the experimental procedure is we want to realize that we're going to have to freeze 6 solutions, okay? And we'll talk about what those 6 solutions are in a second. But what we're going to do before we freeze the 6 solutions, or 2 solutions 3 times each, is talk about the ice salt bath. So you need to make an ice and salt bath. In the freezing point depression experiment, Tim and I showed you, I think Tim did, actually showed you in real life on a video how to make that ice salt bath. If you want to refer to that, you could watch the video again and see that. But I'm not going to talk about that in great detail here. The purpose of this video is to give you a general idea of what's going on, but not to give you every single exact detail. So what we're going to do for our ice salt bath and freezing our solutions and actually measuring the freezing point using the Microlab, which again, you should refer to that video where we show you how to do all of those things, is what we're going to do is 2 solutions, which is first the unknown concentrated lake water sample. And you're going to use 5 milliliters in a test tube. And then just like we show in that other video, you're going to freeze that 5 milliliters 3 times. Make sure that you let it thaw before you freeze it again. So basically, if you just want to put it in some room temperature water, that would be a good idea. I wouldn't suggest heating it up because then it's just going to take longer to cool it down. So if in between each trial, you just want to heat it up using room temperature water, get it so it's not frozen, you can then freeze it again. And you're also going to compare the known. And for your known, you're going to take 0.25 grams of metal 2 plus acetate in 5 mLs of water. And 5 milliliters of water is approximately 5 grams of water because you're going to have to calculate the molality. And you're then going to again freeze this 3 times, thawing it in between each time. So you're going to use the unknown sample 3 times, the known sample 3 times. Again, you can use the same sample and freeze it 3 times, and you're going to find the freezing point depression of each of these. Now, I do not want to go over the how to calculate the experimental Van Hoff factor, but I do want to talk about the Van Hoff factor, generally speaking, the theoretical Van Hoff factor. So we have metal acetate 2, and it's a solid. And when it dissolves into the water, okay, it's going to dissolve, so we just won't use a reversible arrow. You're going to get metal 2 plus aqueous plus 2 acetates aqueous. So there are going to be 3 things in solution. So the theoretical Van Hoff factor is going to be equal to 3. You're then going to compare that to the experimental Van Hoff factor of the unknown, the experimental Van Hoff factor of the known. Based on both the spectroscopy data, the lambda max, and the experimental Van Hoff factors of the unknown and the known, you're going to make a recommendation of whether or not you think you have the correct species in solution. The other thing is, to point out here, you're going to use for the unknown, for the molality, you're going to use the molality of the from the spectroscopy and the conductivity results, and hopefully those all match. If they don't all match, you're going to want to think about which of the 2 to use based on some possible contaminations that might be commonly found in solutions. Would commonly found contaminations be more likely to affect conductivity, or would they be more likely to affect absorbance? That's something you're going to want to think about when you use that experimental molality. So this is basically what you want to do. As Tim said in the previous sections of the video, I am purposely keeping this vague. I'm not even writing the equation for Van Hoff factor or for freezing point depression because this is a project, and that's something that you're going to need to think about as you develop your project. So I want to go back to talk about the experimental procedure. So for the experimental procedure, what you're going to want to talk about is for the introduction. I want to now talk about the introduction. So for the introduction, the things that you want to talk about is a list of questions. However, your introduction should be written as a paragraph, not as a list of answers to questions. So make sure that you formulate this as a paragraph and you touch on each of these things. These questions are meant to guide you in your writing. They are not meant to be a list of answers. So what is the formula for freezing point depression? Why are you using an ice salt bath as opposed to just an ice bath? What is the theoretical Van Hoff factor of your salt? It's 3. I gave you that one. All right. How will you calculate the experimental Van Hoff factor for your unknown and known solutions? We talked about how you're going to do that by actually freezing them. Why is stirring important when you freeze the sample? What is the maximum solubility of your solute in 100 grams of water? You may be able to look those up on Wikipedia, although I just checked and one of them was not available. So if you can't find that, just leave it out. You need to consider supercooling and how it will be accounted for in the freezing point depression. And it doesn't say this here, but freezing point depression is a colligative property. You could talk about what a colligative property is and how colligative properties and Van Hoff factor relate to one another. So that is basically the introduction. For the hypothesis in this section, you want to consider what is your expected result? Well, your expected result is that you should find the Van Hoff factor is 3, because that is the experimental or the theoretical value for the Van Hoff factor based on the fact that your metal acetate will break up into 3 ions in solution. And then you're going to want to talk about your expected results and a scientific explanation for why those results are expected. So what I suggest you do is, as you go through the experimental procedure, the previous part of this section of the video, think about how you would write that in 2 or 3 sentences that express the major points of what is included in all of the things that we discussed. Things such as you're going to use 5 grams of solution should not be in your hypothesis, right? That's not a major experimental point. However, things like the supercooling, that could be there, colligative property could be there, freezing point depression could be there, and how you're going to measure that, and all this kind of stuff. So think about what the most important points are and put those in a few sentences in your hypothesis. So the last section that we're going to talk about is the pH of a buffer solution. And this solution doesn't only contain the metal acetate that we've talked about in the previous 3 sections, but it also contains acetic acid. And in order to use the Van Hoff factor, the Henderson-Hasselbalch equation, sorry, I got confused about what I was talking about here, to determine the pH, you're going to need to determine the concentration of acetic acid. Now, you are doing the buffer experiment basically 1 week before you start doing this experiment. It's the same. I mean, you're essentially doing the exact same thing. So I want to talk a little bit about the experimental procedure first, and then I'll talk a little bit about the introduction and the hypothesis. So the first thing is you need to standardize using KHP. And you're going to want to use somewhere around 0.2 grams of KHP for each titration. And you're going to standardize using sodium hydroxide. So you're going to take 5 molar sodium hydroxide solution that's provided to you, and you're going to make a reasonable amount, I would say somewhere between 100 and 250 milliliters of a approximately 0.1 molar solution. So use your C1V1 equals C2V2, where the initial concentration is 5 molar, the final concentration is 0.1, and the final volume is, let's say, 150 milliliters, and figure out how much of the initial sodium hydroxide you should need. So another way, find V1. Then you're going to titrate again against around 0.2 grams of KHP. It's a 1-to-1 titration. You're going to use that information to find the exact concentration of the sodium hydroxide solution. You're going to do this in triplicate, so you're going to find the molarity 3 times. The RSD of your 3 molarities should be less than 25. If it's not less than 25, you should repeat this and do it again. Okay, so if you have an outlier, you may only need to do one more titration, or maybe you need to do two more. You can consult your TA for advice on that if your RST is higher than 25. Next, you're going to actually titrate your unknown solution. So what you're going to do then is you're going to titrate 5 milliliters of your unknown solution. You can add a little bit of water to bring your volume up, and you're going to add some phenolphthalein indicator. You are going to use the phenolphthalein indicator for the standardization as well, although I didn't mention it before. Note that for the standardization, you're using a clear solution, so the indicator will turn pink when the titration is over. However, the metal acetates are colored to begin with, right? So it may not turn pink, but there should be a clear color change from our testing that you will see. It'll depend on the initial color that you start with. So then you're going to do 3 titrations, and that will give you the concentration of the acetic acid. You are then going to use your Henderson-Hasselbalch equation, which is pH equals pKa. You're going to look up the pKa of acetic acid plus log concentration of acetate, C2H3O2 minus, which you will use from either the spectroscopy data or the conductivity data, or hopefully they're both the same, and the average of all 6 of those trials, over the concentration of the acetic acid, which you are going to find from the titration. Experimental, or the theoretical pKa, which you can look up on the internet. You already did for experiment 18. And then this comes from the conductivity and spectroscopy sections of the experiment. And then this from the titration section. Then you could find the experimental pH, the theoretical pH. Then to find the experimental pH, you simply stick a pH probe into the solution and you measure the pH. You're going to want to compare those two pHs to each other and to the DEC's recommendation for pH. One minor point of contention is that the concentration in the conductivity and spectroscopy sections of the experiment is in molality because of the Van Hoff factor. Here, you're going to just assume that it's molarity. Because it's a dilute solution and because the density of water or the solution is around 1 gram per milliliter, they're close, all right? And instead of making you find the density and do that calculation, we're just going to let you use the molality as your concentration of base. For the introduction, so that's the experimental procedure. For the introduction, you're going to want to write about 300 words, and you're not going to want to write a list of the answers of these questions, but you're going to want to consider these questions as you write your 300 words. So, what is standardization? Why is it important to standardize your NaOH using solid KHP? Solid KHP is actually a very interesting thing. Why are we using solid KHP instead of a solution of HCl, for example? What acid are you going to be titrating? Okay, we talked about acetic acid that you're going to be titrating. What is the pKa of this acetic acid? You can look that up online. In fact, you have that for experiment 18. That's what you did, was found the pKa of acetic acid. The Henderson-Hasselbalch equation we just talked about. How are you going to use that to calculate the pH of the concentrated lake sample? We just talked about that as well. So in your introduction, about 300 words, you're going to want to address each of these questions and kind of write it out in paragraph form. You may want to add some other stuff that you think of as well. The next thing that you need is the hypothesis. So for the hypothesis, you're going to assume that nobody has been contaminating this lake and that the concentrated sample has a pH between 4 and 9. Now, if it has a pH above 7, that would be very surprising considering that it's got acetic acid in it, but okay. So it should be, between 4 and 7, really, but you're going to assume that it is between 4 and 9. For the next part, for the expected results and the scientific explanation of those expected results, so the expected results are that the pH would be between 4 and 9. why are you going to expect them to be there? Well, acetic acid is acidic, so that's a pretty good hint. But as we talked about the experimental procedure and the titration and the standardization and so on and so forth, you're going to want to think about what are the most important details, and in 2 or 3 sentences, write out those most important details that explain what you're doing. So you don't want to put every single little detail, like how many milliliters you're going to titrate or any of this kind of stuff. You're going to want to focus on the major details about the stoichiometry of the reaction, about how the standardization is used, and so on and so forth. So that will help you with your hypothesis. So as usual, the Prelab contains a chemical hazardous and waste section. And although we're determining reasonable concentrations that the DEC allows in these concentrated water samples, this is not realistic, okay? We don't want any of these metal ions going into the water stream. Said another way, don't pour them down the drain. So make sure that anything that has a transition metal acetate salt is ending up in the waste container. So that will include all of your stuff of our for spectroscopy, for conductivity, for the Van Hoff factor, and for the titration. So essentially, all of these solutions need to go into the waste container. Also, if you have any leftover sodium hydroxide solution, that's going to have a pH that's too high to go down the sink. So let's please also put that into the waste container. Be especially careful with the 5 molar sodium hydroxide solution, as that could cause major problems, especially if you get it in your eyes. So make sure you're wearing your goggles. If you get any on your skin, make sure you rinse it off quickly. I just wanted to make a couple quick words about citations. So if you insert a figure or a picture, if you look up a value of the pKa, an explanation of the theory of how an instrument or scientific principle works, any of these kinds of things you should cite if you look them up on a website or in the lab manual. And how you could cite them is simply, if it's from the lab manual, General Chemistry 2 lab manual, page 57, it's fine, or whatever page you used, of course. Or if you picked it from a internet source, just the web address. So you don't need to use like MLA style here or any of this kind of stuff. You could just roughly cite your work based on if you took it from an external source. Of course, even if you took something for an external source, like the theory of how a spectrometer works, you can't copy and paste it, okay? You can't copy and paste it and then cite it. You have to write it in your own words. So make sure you're not copying and pasting anything out of the lab manual, or typing directly anything out of the lab manual, or from internet sources. It does need to be your words, but you can take ideas from other places. Just cite those ideas.
The last thing we want to talk about is how to perform a back calculation. While doing this experiment, you're going to find some things are true. You're going to find that the absorbance and the conductivity of the unknown is too high for your calibration curve. Said another way, if you measure the absorbance of the unknown solution or the conductivity of the unknown solution directly, you'll find that it's over 1 absorbance unit, or that its conductivity is over 2000 microsiemens per centimeter. So that means in order to get it onto our calibration curve, we're going to need to dilute it. So if we dilute it, how do we figure out the concentration of our initial solution based on the concentration that we're going to calculate using our calibration curve? Well, to help you with that, I've created a example of this type of problem. So we found that the absorbance of the unknown was too high. So we had to dilute 1 milliliter of the unknown in 9 milliliters of water in order to get it on the 0.1 to 1 range. Once we got it on the 0.1 to 1 range, we measured the concentration and the calibration, or we measured the absorbance, and we used the calibration curve to get a concentration of 4.5 times 10 to the minus 5 molal. So now I need to convert from this concentration back to the initial concentration of the actual unknown solution. So to do that, I'm going to use a variation of C1V1 equals C2V2. In this case, I'm going to say C unknown times the volume of the unknown is equal to the concentration of the diluted sample times the volume of the diluted sample. So the concentration of the unknown is what we're going to be solving for, so that's going to stay as a variable. The volume of the unknown is going to be how much of the unknown we used to make our sample that ended up on the actual calibration curve. So in this case, it will be 1 milliliter. And that's going to be equal to the concentration of the diluted sample, which, thanks to our calibration curve, we know is 4.5 times 10 to the minus 5 molal. And we're going to multiply that by the volume of our diluted sample, which was 1 milliliter of the concentrated plus 9 milliliters of water, for a total volume of 10 mLs. So if we divide both sides by 1 ml, it'll cancel out on this side, and on this side we're essentially multiplying by 10 and divided by 1, but our units of milliliters will cancel out, which is important. So we'll find that the concentration of our unknown, the initial sample that's provided in the lab, and the number that we need to report on, is 4.5 times 10 to the minus 4 molal. So it's important that you're able to do this because you need to report based on the concentration of the actual unknown solution provided in the lab, not the concentration of whatever sample you actually measure that ends up on your actual linear range. So you'll be able to perform this exact same calculation, of course with different numbers. You won't necessarily use 1 milliliter and 10 milliliters and have a concentration of 4.5 times 10 to the minus 5 molal, but you should have similar numbers or numbers that you can substitute in the same way in order to calculate the concentration of your unknown from the concentration of the diluted sample that actually falls on your linear range for your calibration curve. So if you've made it all the way through the full hour of this video, we appreciate your dedication to doing well on the experiment. If you've watched the portions of the video that are related specifically to the things that you're doing in this experiment, we appreciate that as well. We hope that this video will help to set you up for success for this experiment, and I just want to remind you again that if you do hit a roadblock and are unsure where to go, you can not only ask your other group members for advice, but you are welcome to come to staff and TA office hours in order to get advice if you're stuck doing the experiment. So thank you for watching the video, and good luck on your project.